Hey, well, by my clock, we are at 12:30. Philip, I want to just check your audio real quick. You want to give me an audio
Sure.
test?
Can you hear me?
Okay, I've got you. You've got good audio. Okay, so we're at 12:30, so we'll go ahead and get started. My name is John Mann, and I am an assistant professor at Michigan State University, and I host this webinar series. It's called Innovations in Agriculture and Rural Development, and the series is sponsored by the North Central Regional Center for Rural Development. So I want to welcome everybody to today's webinar. The title is Soil Functional Maps for Crop Management and Planning. So before we get started, I want to point out just a couple of quick items real quick. And so it looks like most of you have done so, but if you'll just take a quick second, if you haven't, and fill out the poll question, that way we can get an idea of who our audience is. And next, at the conclusion of the presentation, so we're going to go through our presentation, and at the conclusion, if you look at the bottom of the screen, there's a chat box, and so that's where you can type in your questions. And please feel free to enter your questions at any point in time, but we will get to the question and answers at the end of this session. So the next thing that's going to happen is I'm going to change the screen a couple of times, and so it makes it convenient for our setup. So I'm going to demonstrate that, and this will get us to our PowerPoint presentation. So we'll give the screen just a minute here to load. Had a little bit of internet delays here at Michigan State, so that's gotten reset. Okay, so again, I want to thank everybody for participating today, and I want to introduce Dr. Philip Owens. He's an associate professor of Pedology and Soil Geomorphology in the Department of Agronomy at Purdue University, and he's going to tell us more about the soil functional maps for crop management and planning. So, Philip, go ahead. It's all yours.
Okay, thanks, John. Um, Thanks everyone for listening, and hopefully we'll learn something. And I always love giving these talks to different groups and different audiences because I always learn something when I talk to the different groups. So I want to talk a little bit about when I got to Purdue. I started thinking about research and what direction I wanted to go, and I started thinking about what do people really want to know about soils. And so from talking to people, visiting, thinking, I came up with some thoughts that people really want to know what the role of soil is in yield variability. They want to know what's the role of nutrient release, nutrient responses, soil plant relationships, water storage availability, and how to manage their soil for long term sustainability. So I can't answer all of those questions, but I thought with my skill set and what I understand about soils and landscapes, I could start providing data so that people can utilize this data and information and spatially explicit data so that we can understand the role in soil to answer these questions. And so I really need to work with lots of different people to answer these questions, but I saw my role as providing the baseline and the fundamental information that will allow us to have a better understanding of some of these processes. So when I was thinking about what our current available information is about soil, it's in the USDA Soil Survey, and these soil surveys were created by scientists in the field using aerial photography and capturing the soil landscape relationship in polygons, which the polygons are related to taxonomy and morphology. And they're very good base maps, and they've been good for management. But where we are in the data demands and the data needs, we need more spatially explicit information to help us understand the role of soils. And so you can see on this figure the some of these boundaries uh, show different surface reflections from this aerial photograph. So I wanted to dig in to find out one, um, what are the soils in these areas, and also how can we spatially represent the continuum, because we know that at these lines the soil doesn't change abruptly as they're represented on the map, and the properties within those soils do not change abruptly. They change in a continuous fashion. There's also with the way the maps were created, there's up to 2 acre inclusions or 0.8 hectares that just physically couldn't be represented just due to the technology of the way the maps were created at the time. So I wanted to think about how to spatially represent the the soil properties and how can we combine those properties to utilize that for a particular function. And yield is one function. There are many functions. I started out initially working with hydrologists and ecologists, and then started working more on the agriculture related issues. So the soil maps are made, the mapping units are described from the taxonomic descriptions that you saw in the previous slide. So they illustrate more how soils look and classify, and they, because of the way they're made, they lack the ability to incorporate the landscape within the map as well. Although it's implicit in the maps because it's based on a Catena concept, it's certainly there's some more detail that we could provide by using the terrain as well, and focus more on how soils work the same rather than how they may look differently. And so, one of the things that's very important, especially when you're thinking about the soil's function, is not just the physical properties and the chemical properties, but it's also with the water. Because if you have a soil that's got all the nutrients the plant would need, if it doesn't have the water, it can't utilize the nutrients. So there's some relationship between these two that we're trying to explore and utilize that connection to further explain some yield variabilities that we see across the field. And so one of my first projects that I worked on was using geostatistics. And so uh, I got some funding, and we grid sampled a field in southern Indiana, and we did intensive sampling at multiple depths at about 20-meter spacings, and that was the direction that I was planning to go when I first got started. So this is one of my first projects. We looked at the non-exchangeable potassium using tetraphenyl boron method. And so this is the resulting map of the field at 3 depths. You can see the 5 centimeter depth, 30 centimeter depth, 60 centimeter depth, and then the concentration of potassium we found there from non-exchangeable. And here was the exchangeable potassium, and you can see that on the edges of the field, the exchangeable potassium is higher. Again, the 3 depths. So what I also found was that you needed to sample the soil approximately 100 feet to capture the variability we were seeing in the soil properties. And so I show potassium here, but we also did texture, carbon, depth of soil, and some other measurements that we made across the field. But almost all of the properties, the sampling distance was pretty short, and so it'd be pretty costly to sample this field and use these kriging techniques to interpolate between the points. And the other interesting thing, what I learned most from this project was something I should have already known, was that topography is a big driver when you're looking at soil variability when you have the same geologic material that you're working in. And so this is one of the algorithms that we used, topographic wetness index. Some people call it the compound topographic index, but it's the upslope contributing area over the tangent of the slope, which these colors are representing. The high wetness index or areas here where it has a low slope, the blue, and so that's saying that water is not moving off of this landscape, whereas the areas in green are showing where water is moving off the landscape based on the slope, which that was relating very well statistically to the properties that we were seeing. So what I learned most from this project was that topography was a big controller of the soil properties, but also that it's very costly to do intensive sampling, and I was trying to think of a way to do this on a grander scale but maintain that relationship that we've understood in the soils for a long time. This is the 1934 Catena concept by G.A. Milne, and what I saw from my that first project was that soils do follow this repeatable pattern based on topography. And drawing again from the older literature, thinking about Hans Jenny's 1941 state model, it says there's 5 factors that affect a soil at a given location, and the 5 factors are climate, organisms, relief, parent material, and time. And so what my approach was to try to hold those 4 factors constant, but just work on the relief uh, factors so that we could make a predictive tool. And so relief is easy to the data is easy to come by because of we have good digital elevation models now, and we can digitally represent the topography. And so topography alone is really not what causes the variability of soils. It's the topography that causes the redistribution of water over long periods of time that causes patterns to develop because it's related to the processes that cause soil to vary across a landscape. So it's really the water. And we're trying to follow the water because the water is linked to the processes that cause soil to become different. So this is the mental model that the soil survey uses. This is a block diagram, and this is how the soils were mapped across the field, which is exactly how soils do lay on the landscape. But I started thinking about properties rather than putting soils into mapping units because the properties, I believe, if you're in a fairly homogeneous geologic material, that the properties are predictable and you can follow those across the landscape and make those predictions. So what we started doing, this is the first project we worked on, and we're looking at Howard County, Indiana. It had a pretty uniform parent material across much of the areas. And so we're looking at the relationship between the soils and how we could use the relationships to begin predicting properties. So what we did on our first project was we took a digital elevation model up on your left. We ran the wetness index that we talked about from the previous study, looked at slope and a couple other terrain attributes, and these are all just derivatives from the original digital elevation model, and overlaid it onto the soil survey map. And so from that, we used an application called Knowledge Miner, which is in a software called SOLIM. It came out of University of Wisconsin. Zing's work. So we extracted these pixels and started looking at the relationship between the different terrain attributes. Like this one on the left is the altitude above the channel network, and you can see the value where it peaks is about 0.5. For the yellow Fincastle, it peaks at about 0.8. We looked at things like curvature, which we didn't see any difference between in curvature, which on a low relief flat landscape in Indiana we wouldn't expect to. We're doing our explorations. And then we looked at wetness index. Again, we saw a pretty good separation between where these two particular soils would occur. And so from there, once you know how particular soils will be within these patterns on the landscape, you can write if-then statements. So this is a very simplistic example of how it works. You can say if the wetness index is 14, then assign Brookston. If it's 10, then assign Fincastle. And you can use multiple terrain attributes to do this. So this really, what you wind up with in the end is a membership probability for every pixel on the landscape. So if the wetness index happens to be 13 instead of 14, it's not going to be 100% membership because it's going to vary from the rules that we set. So we're writing some rules to describe the landscape. And so one of the resulting products is this probability or fuzzy membership map. So from our rules that we wrote, you can see the red in the center in this Brooks says 100% Brookston given that the rules we wrote were correct. And so now we have a probability map that shows every pixel on the landscape has a unique probability of being a particular class. And so once you have that, you can use this equation to predict the property. So the Dij on the far left is the predicted property that would be resulting from the map. The DK is the property that we would set for 100% membership. So if we know that a particular soil is 3% carbon, we would put 3% carbon in the DK. And if we is SK over SK is 100% membership, then the value that we set will be equal to the value that we predict. So that allows us to um, move across the landscape and adjust the property predictions as we move across the landscape. So an example, we were working in a watershed in southern Indiana, and this you can see the center is the county boundary, two different decades of mapping, and so we used this process to make a soil depth map that I'll show you in the next slide. But we validated the map with 127 georeference field observations. We looked at what the soil survey had, the representative value in the soil survey versus what we measured. It was an average difference of 57 centimeters. And when we used our process, the terrain attribute soil mapping predictions, we were an average difference of 22 centimeters. So we improved the map and made a property map. And what you're looking at here is the soil depth. And so the dark browns are the deep soils on tops of the hills. The side slopes are the shallow depths, and then the floodplain again gets a little bit deeper. So we're following the landscape, and we found very good validation from our predictions. So then I started thinking about yield relationships, and so with this process, we've refined it more over time. But this is some maps of soil properties. We're looking at available water holding capacity. On your left is the soil survey product, and on the right are the continuous predictions that we've made for this particular farm. See that it's certainly following the landscape. These are the properties we made for cation exchange capacity, organic matter. And the nice thing about this process is if you have data, you can predict anything. So if we wanted to know what potassium was, if we have some potassium data, we can set that as our DK. Um, so it's very flexible in that respect as well. So we started looking at some yield data across years. And so this is corn yield for 208, 209, and you can see the blues are the higher yields, the lighter colors are the lower yields, and this is the same field across those 2 years. And two more subsequent years, you can see the yield variability is quite high across years. But from that, looking at the yield data, you can do things like make a proposed strategy management index. So there are some parts of the field that we found in our lots of studies that we've done that the yield is stable across years in particular areas. And so you can count on those particular spots having a pretty consistent yield across years. What we all found in other locations is you have quite variable yield in some locations. And so these are the areas that you would focus on, and because you can make or lose money based on the highly variable yields years, and try to understand some of the processes of why these particular areas, what is it that's causing the low yields? Is it too much water, not enough water? Is it a fertility problem? But it gives you a way to link the processes that's causing the changes in yield across years to what the actual soil is in a continuum. So as we've developed this further, we're using it for multiple different processes. We're starting mapping in Central America. We're mapping Honduras, Nicaragua, and El Salvador from a Howard Buffett grant with the Catholic Relief Services. And so as we've developed this, we've gotten some better algorithms that we're using, and some that we've developed here at Purdue we're using to map. But as a just the logic that we're using to map not only in the U.S. but also in other countries. We use legacy data, and then we do some landform classification, which is a newer process that we're using, and I'll walk you through that just a little bit. But you have to know what your geology is because that's really what the soil inherits. If a soil was deposited as sand, it's going to be sand. If it was deposited as clay, it's going to be clay. So you have to understand what you're starting with, um, and then from there, you can utilize the terrain features to help explain the property and make the predictions. So once we get this, or basically our class map is the patterns that we recognize in the landscape. Because really, I would say what this boils down to is pattern recognition, assigning numbers to the patterns, and then allowing that to be extrapolated continuously across the field. From the class map, we also apply the terrain attributes, and then we use the automated landscape inference model, which is unique algorithms that we developed here. One of my graduate students, Jeanette Ashtikar, did that, and from that you can develop the continuous property predictions. And I'll show some examples. This is one of the newer things that we're using now. It's called the Geomorphon. It's an add-in in GRASS software, which GRASS is a free GIS, more command-driven software to map. And so this was published in 2012 from Jakowitz and Stemniski, but we started utilizing this to help us pick out the patterns that we find in the landscapes, especially when we're working outside the United States. We first tried it on Colombia, but as part of the Buffett grant that we're working on, we started looking at the Nonexchangeable watershed in Honduras. We have approximately 10-meter DEM that was created from scanning a topographic map, paper map, and making it digital. And so we're working with scientists in this area to try out this procedure. And so what we did was made continuous property maps of the area based on some data that they had. And here's some examples of the sand content, the silt content, clay, cation exchange. And so we several different, we had depth of soil as well. But here's an example of the soil organic matter map. And you can see from this particular area, one of the powerful aspects of this procedure is you can keep uh, zooming in and getting the individual pixel predictions from the map. And we're zooming in again. And the most exciting thing is you can start getting zoomed in enough to see small fields and how the properties would change across the field. And so this procedure is limited by the resolution of the DEM. So if you have, like when we were mapping in Colombia and Afghanistan, we only have 90-meter pixel resolution, so that's the resolution which we can make predictions. Here in Indiana, we have 1.5 meter pixel resolution, but it turns out that's actually too much information. So we downsample to about 8 to 10-meter pixel resolution to get. But from these properties, you can begin. We make the property maps, and then you can combine these properties to start answering some questions. And we also try to create the uncertainty with the maps. So we want to be honest about the maps that we make. You can see the map to the lower left is the predictions, and to the right and the left, or to the right, are the uncertainty maps. So you can see the areas in the blue is basically the range of the data, which means we're not really sure what's in the floodplains of those soils because we don't have data. But at least a user from that information will know to look at that a little more closely. So I think the uncertainty predictions with the maps is extremely important. This is an example of that watershed, thinking about what is a crop suitability index. So if someone wants to manage this particular property, you can combine the properties. So on the right, we have slope, depth, different weighted averages of that to make a
Uh-oh, I think we lost our presenter for just a minute, so let me work through this technological problem and get him back online. Hey, Philip, are you able to turn your microphone back on?
Hear me, John?
Yes, yes, I can hear you. We've got your audio again.
Okay, good. All right, so we're good to go again, right?
Yes, yeah, we're good to go.
Okay,
Go ahead and
okay,
pick up where you left
great.
off.
So anyway, so this map, by combining properties, you can start making some management decisions. So I think for the future, I think we are working on how to automate this soul mapping process and try to make it where we can do large areas now, but it's time consuming. It takes people going through all of these steps step by step. And I think the one of the things we're also working on is um, how to input more data into the map, especially for properties that are dynamic that would change across years, like maybe pH, nitrogen, some of the even carbon to some degree. But get real field data, put the field data into the algorithm, and then recreate the map so that we're continually building this resource and developing a better predictions of the soil property. One of the things I hadn't mentioned that we are also developing ways to get smart sampling so that you could get a map of where you could take a sample that's where that sample would have the most power to be extrapolated across the landscape because we understand from previous research over the last 70 years why soils are changing, and so we can incorporate that into the smart sampling strategy. So you minimize your sample but get the most power out of that particular sample. And the real power, I think, is coming when by working with others. Um, I'm working with Brad Jorn here at Purdue, who's got a really good nitrogen model, um, because I think one of the limitations of the models is the soil data input, because as we saw from the previous slide, once you change the mapping units, the values associated with those mapping units change on a discrete line when we understand that's not the real world. And so incorporating better data into the crop models so you can do things like what if tools. So if you are uh, in the first part of the season with your corn and you want to know, could you put on nitrogen, would it boost the yield and pay for itself? If you have good data and a good model, at that point you could run the model and say, what if I have a dry year? What if I have a wet year? What if it's an average year? Would this application of nitrogen, would it pay for itself, and would I benefit economically from that particular application? The other thing that I think is extremely powerful is thinking about this yield variability across years, looking at the economics of what are the input costs. Are there certain parts of the field that are losing money consistently, and if so, are there things that we could do to adjust that, and so at least you would know or be able to minimize your losses by using some of the precision tools and some of the crop models. And so it would be good to see your map a map of your field about, are you making money, are you losing money, and if so, why? Are there things that we can do to adjust that and make a more profitable farm and manage for profit rather than just manage for yield? And so um, many of you seen this kind of results. This is from Brad Jorn's work, where some of the generally the soil mapping units follow some of the trends, but in some places they don't. Like in the MA2 up at the very top, if you're not if you're trying to manage off of the mapping units, it will be hit or miss in some locations, in some areas. But if you're start thinking about incorporating the not only the soil properties but also how water's moving on the landscape, because what we're doing, water redistribution is implicit in the model, and so from what we're seeing, we're getting pretty good results about uh, how that's relating to soil function by combining the properties to target specific questions. And in the case, I think yield is a good question to focus on. So that's what I have to talk about, and I'd be happy to take some questions.
Okay, so I'm gonna change the screen real quick, and we'll get this set up for us to do question and answers. So as I'm going to let the slides also reload. So in the chat box, go ahead and type your question in below. And so there's this little space for you, and then just hit enter, and it should populate the question. So as we're waiting for a couple of some folks that are typing, looks like we've got quite a few people that are typing stuff in. Philip, I'm going to ask you a question, the first question real quick. And so kind of given where you are right now with the technology, could you expand just a little bit more on what the next step is for you? Basically what do you need? What's the next step for you with the technology development?
Uh, so we have a good process in place right now, and I think it really needs to be streamlined a little bit. So we're looking for ways to basically fund people to do more research on how to get it automated, because we can do it, but it just takes a lot of time going through this process at multiple steps. Where um, I really believe, since everything's in place, it's going to take a little bit more work to get it automated, and then also once it's automated, then finding ways to incorporate more and more data that's collected on farm rather than sitting in a folder. If it can be placed into the model to improve the predictions, then I think it's going to make a better product in the end.
Hey, thank you for that. Okay, so our next question is, and I'll just start reading these one at a time. Were you using apparent water table data or seasonal high water data?
No, we haven't. We don't use that. We're using primarily the train algorithms that's describing how water's flowing. But once we get the patterns recognized using the train attributes, we can incorporate some numbers for the water table, so we can understand the water table, make predictions of the water table, as well as the physical properties and the chemical properties.
Okay, thank you for that. Okay, so the next question is asks, can we use electrical conductivity bar to map soil for properties as texture and moisture?
Well, there's the EC work that I've seen and been involved in. It's hit or miss in some cases. I've seen some really fantastic maps using ECs, but what it depends on is the soil moisture content. So if you take your EC at a period of time where it's really dry, you may not see any influence, or if it's really wet, you may not see the AC changing across the field. So there's some really ideal times to take it, and it does tell you something about the subsurface properties because it is controlling water. And as you concentrate or as you decrease the water, you concentrate the salts. So it's about the salts in the water, and so in some cases it works really well, and in some cases it doesn't work so well. And EC, I would also say, is something that's pretty variable. So we have not tried predicting EC with this technology.
Okay, thanks for that. So the next question, what variables are working best in low relief terrain?
The best thing that we found for the low relief terrain is the wetness index. Um, but it's so that because that's really even minor differences in elevation are resulting in big changes in soil because when you get the water on a slope, it's going to go downhill, it's going to collect, and that differentiation of water is a huge driver of how the soils are changing. And some terrain attributes that we use don't necessarily relate to processes, because if you have a soil on a slope of 0 to 1% that's next to a stream, and a soil that's 0 to 1% on top of a hill, those aren't the same soils. So we have to use something like the altitude above the channel to separate those two soils to make them unique patterns. And so a soil next to the stream would have a low number. The soil on top of the hill would have a high number. So within our if-then statements, we would say if the altitude above channel is high, then put it on the top of a hill. If it's low, put it next to the stream. And so it's a lot of the reasoning of some of this that we have to put into writing the rules.
Okay, thank you for that. The next question, what scale of mapping are you doing your prediction on the farms? I guess what are you basing that mapping on?
Okay, so the scale that we're mapping is really related to the resolution of the digital elevation model. And so we have to think a little bit different. So what we did on the farms that I showed, the farms in Indiana where we did the CEC organic matter, that was at a 5 meter pixel resolution, which that's about 15 feet. So every square on the farm is a 15 foot by 15 foot square, and we're making predictions of the properties based on that resolution. That answered the question.
So that's actually a good point. If you've got a follow-up, go ahead and feel free to type that in or a clarification on a question. So thanks for that response. Next, could you highlight if site-specific management could be linked to the soil functional mapping, considering within field yield variability?
Yeah, so the way I think about it is it is extremely difficult to predict yield because we know that the climate is one of the biggest factors that affect yield. But what we can do is highlight the areas where the yield is variable across years. And so there's also areas where yield is stable across years. The variable part of the field is where you're going to make money or lose money. And if you understand the reason why the field is variable, you can potentially manage that particular area and either improve it and improve the yield, or you could minimize your inputs to save you money so that you're thinking about it more like inputs and outputs. And so having that spatially represented as a layer on the tractor as you're driving across the field, you can adjust your inputs, adjust your seeding rates, but knowing where that is and knowing and having some understanding of why that particular area is a variable, I think is an improvement. And I also think that putting this data into crop models so that we can start asking some what if questions. If you're mid season and it looks like you're going to have a drought, you can ask the question with the model: would it make sense to utilize a particular strategy to increase my profit or increase my yield on what we're doing? And if then you can answer yes or no, and at least make an informed decision as you're moving forward, um, rather than with less information.
Oh, thank you for that. Okay, next question. How can we use this approach in a national mapping program? Could a small watershed be the basic unit of study?
Well, the thing is with this, once you get the model set up and you're in a particular geomorphic surface, and you can apply it across a very large area. And so the places where it doesn't work very well is where you have a parent material or a original geologic material that's really heterogeneous. So I think of places like the Mississippi River floodplain where I've augured it into a clay at one spot and I'll walk over 20 feet and auger into sand because that's very different because of the way the river deposits the materials. It doesn't work very well in those particular locations. Where it works the best, and I'd have to say for those particular locations, it's still going to take people on the ground augering holes to use to get a good soil map. In places where it's working well are places like in the Midwest and the Corn Belt, where we can delineate the different geologic materials, and then on top of that, we can use the terrain features or terrain algorithms to make these pattern predictions. So I think it very easily can be done at the national scale if the will was there from the leadership to do this.
Thank you for that. Okay, next question. Do you always use 10-meter DEMs, or have you mapped with 1 meter or 3-meter DEMs produced with LiDAR?
Oh, so I have a funny story. I When I started this, I got a 3 centimeter RTK GPS uh, and made an elevation map that was it was incredible. And so then we ran our terrain attributes on this high resolution map, and we found out we had no relationship between the topography and the soil because we were mapping cow tracks and tractor tracks and things that had no relationship to what was below ground. So what we found from that original study is we had to use a resolution between 5 meters and 10 meters to actually capture what the soil is below ground because it creates too much noise when you use resolutions that are finer than that. So really, from what we found, at least in Indiana on the till plane, 5 to 10 works best. I think you can get away with coarser resolution if you're in steep sloping areas, hilly areas, but um, too much noise with the 1 to 3 meter resolution, and not enough resolution if you go more than 10. So our sweet spot was between 5 and 10. So we try to use 5 most of the time.
Hmm, that's actually pretty funny. Okay, next question. Do you take aspect effects into consideration in mountainous areas?
Absolutely. Aspect is huge in mountainous areas, and that has to be part of the model when you write the if then statements because it makes a huge difference because the energy differences are are represented due to the aspect in the mountainous regions. On the low relief till plains in Indiana and in any low relief area, we have not found that aspect has has any relation because since it's so flat, the energy from the sun is close enough that we're not seeing any big differences.
Thank you for that. Okay, it looks like the next next question may actually be a comment related to an earlier question. But Philip, I'll see if you have a comment on this. So EC measures electrical conductivity that is affected by moisture, clay content, bulk density, and the solution salt composition.
Absolutely, I agree with that 100%. But when you're using EC to map a field to explain the soils, it's very important to consider the moisture content at which you are utilizing the EC meter because if it's very wet, your salt contents are diluted and you don't get the resolution that you're trying to capture by making the map. So there's a sweet spot that from my experience, there's a sweet spot that does provide a good map, but there's also there's moisture contents where you don't get the resolution that you're looking for, or and you're not getting the product that you're interested in.
Okay, thank you for that. Okay, next question. I may mispronounce this, but why use SOLIM as opposed to other DSM method?
SOLIM was the software that we used, but really we don't use that anymore from our with the current work we're doing. We've written our own algorithms to do that. But I do like the that knowledge based inference approach where you're identifying the pattern on the landscape. So we understand the patterns, we populate the patterns with data, and then we use that uh, probability membership to follow the topography on the landscape to make the predictions, since we understand that topography is the big driver. Um, but I think there's multiple ways to do it. This approach that we started out with, because it was already there and usable, but we've moved on from that a little bit, and and I think there's a lot more work to be done, and I think the future will see a lot more development in these methods.
Hey, thank you for that. Next question. Without a correlation study, does one not know what to do with, or I guess what to do with the EC is responding? In humid regions without salts, bulk EC might respond primarily to texture and moisture.
Yes, I agree with that 100%. And so in some cases, um, I've seen, the you're looking at the subsurface of the soil, and in some cases where the soil texture is changing, where the clay is changing, the water content's changing, and the salt content's changing, and you pick that up. In some cases, it doesn't represent it as well. So for me, it wasn't a, a method that I thought was consistent enough for use for what I was trying to do, and it does take people on the ground to take those measurements, and I was trying to do something that would be scalable to larger regions.
Okay, thank you for that. All right, so the next question. Um, the SSUR geomaps can also be displayed in terms of organic carbon content, clay content, the location of water tables, the native nutrient potential, catatonic exchange, and more. The press release for your technology seems to indicate that the SSUR geo data can't do that. Seems as though your map products use logarithms to refine SSUR geo info. Is that correct?
So when you saw the first product that we worked on, that was the case where we were refining Sergo to one is to eliminate those artificial lines in the landscape where the properties change from say 1% to 3%, and that it's one number that represents the whole entire polygon. And so we know that's not realistic. And so our first project was to see if we could refine that and make continuous predictions with Sergo. And in some cases, if there's no other data available, we'll still take the Sergo as the base information and refine that using the estimates. But but the nice thing is, if you have numbers that you've taken in your field, you can incorporate them into the model and refine the predictions that are not relying on estimates, but actually relying on real data. So the answer is yes and no.
Okay, thank you for that. All right, next question. How safe and confident are we while using excuse me, soil class maps in field scale yield variability assessments?
Well, from what I've seen, Sergo in some cases captures the variability pretty well, and in some cases it doesn't, because I think they were created for one, with the way it was created with a pencil on an aerial photograph. You couldn't draw a bubble small enough to put a letter in if it was smaller than 2 acres. Um, but in some cases it works well. In some cases you'll have multiple mapping units that function the same, although they are mapped differently. So trying to understand that complexity is a little bit challenging. And the Sergo mapping units do follow taxonomy or morphology, because that's the linking, that's what it all refers back to. and I know sorghum was created for use and management as well as taxonomy and morphology, but still there's some underpinning of that, just looking different and mapping it different versus what are the properties, because the properties are really what people are interested in when they want to use the data. They want to know what are the properties, they want to know how do they change across a field, and to best represent that, I think we have to go away from a polygon based map to a continuous map. And we have to do our best to make the soil property predictions as accurate as possible, use as much data as possible, because we know that the sorghum products are estimates. People are populating these today. Sorghum also, if you look across county lines, some counties people did a where they were splitting everything that they saw different, making a very detailed map. In some cases, they were lumping lots of things, and so trying to get a uniform product with properties is extremely important. And I would never. Also, I want to leave you with this, that I never advocate getting rid of the Sergo polygon, because much of especially taxes and other issues are related to the Sergo polygons. What I'm proposing is an alternate product that helps understand, manage, utilize in crop models to make predictions about how a soil is functioning.
Okay, thank you for that. All right, I think we've got one more question. And he asks, if you make a universal model which predicts the soil series of the whole world by considering the different scale of every variable, how can you actually see that?
Um, I don't think that I would ever even attempt that, because when you're thinking about series are very specific, and they.
Philip, I think we lost your microphone. Oh, try to get him back real quick. Apologize about these technical difficulties we've been experiencing. Since we just had the one question left, maybe it looks like we've got a couple of folks typing.
Okay, John,
Are you back?
can you hear me now?
Oh, okay, yeah, we've got good audio.
Okay.
Go ahead and finish your.
Okay. So I would not attempt to map the world in series, but I think we can map the world with properties. And the reason why I say this is because I think there's a new philosophy and different paradigm on how you map. And I've working outside of the United States, I think it's we don't realize what a resource we have with the base information we have in soils. You go outside the United States, the very coarse maps, of course, and you really can't manage it, because we need to make maps at the resolution where people will actually make decisions and actually need the information. So properties is much easier mapping than series, or much easier mapping than the mapping units that are in Sergo polygons. Um, but the way I have been thinking about mapping is that in areas when we have limited data, there are a lot of experts in the field that can help populate the version one map of these areas. And so I'm thinking about maps in the way you would think about a software. You have version one with maybe it's some expert knowledge about what the carbon content is on a particular area because you have no data. Version two, you would realize you had no data, you go collect it. Version two would incorporate that new data. Version three through however but it builds a platform from where you can start putting data and capitalizing on the data that you're collecting and making it more useful over time. And we currently don't have a way to do that, um, other than some of the geostatistical tools. And so those are not affordable outside the United States. But if you have a farm in the U.S. and you collect samples every year, you could eventually, over time, begin to get some physical properties. But again, the chemical properties are going to change over time, and you need a way to spatially represent those chemical properties to understand the function of your soil.
Okay, thank you for that. I apologize. I think I prematurely changed the screen, but it looks like maybe we've got two other questions. One, I think, pretty straightforward. Where are publications related to this? What publications would you point somebody to related to this topic?
We've got some. You can send me an email, and I'll send them out to you.
And then it looks like the last question here says, are terrain parameters enough while predicting soil properties at a landscape level?
If you have, it depends on how large of an area you're talking about. But if you have a common geology or geomorphic surface, which those are not usually too extensive, then I think using terrain, picking up the patterns, it works well. But every time you switch to a different geologic unit, you have to redo and reset up the model because that geology is critical. It affects the texture, the sand, silt, clay. It affects the minerals that are in the soil, and there's lots of ancillary properties that go with that, like the hydraulic conductivity. And so you can do once you do a model setup, I feel pretty comfortable going across uh, the region where the geology is the same. But once you switch, then you can't really extrapolate it beyond that. Um, and the other thing is, as I said previously, if you're in a geologic unit that is really heterogeneous and it's not very uniform, then also you have to think of other ways to go about doing this because it's not going to be applicable because the geology and the relief are the two big drivers on how soils are different within an area like a state. Um, but once you start getting also in climate gradients, like when we're working in Central America, we have to think about going from the bottom of a mountain to the top of the mountain because the climate's different at the top of the mountain, much wetter. So we have to also delineate the geology, the climate, and then the topography as well. So it just takes a little thought about what's going to cause these soils to be different, and then use digital data to make them.
Okay, I think we have time for maybe one more question. And the question is, have you had any luck with satellite imagery?
So we've tried using remotely sensed information from vegetation indices like NDVI, and because that is climate driven as well as soil driven, we don't get enough consistency across years. And I know there are a lot of people who are using NDVI looking at the 10-year averages or combinations of 10 different years or 20, um, and getting some spatial predictions. And I think that is it's good because it does show you some variability of the yield across years. But I think when we're thinking about the future and where we're going to go and what sort of tools we're going to want good soil data to put into models so that we can ask different questions. The other thing is we are trying to incorporate some remotely sensed information from land use into our if then statements because we understand that a soil that has been under forest and is still a forest is going to have different surface properties than a soil that's been farmed for 100 years that's sitting right next to it, even though everything else is the same. So we're working on that for future applications to try to understand some of the dynamic predictions. But so we have the ability to understand land use. We don't have the relationships of how does a soil surface change when you change the land use. So hopefully in the future we'll be able to something about that too, or maybe one of you listening here can figure that out.
Okay, well, we're going to go ahead and wrap up this webinar. So before I do anything else, I want to give a big thank you to Dr. Philip Owens from Purdue University for the presentation. It was very informative, very interesting, and I really appreciate you taking the time to participate in our webinar series.
All right, thanks for the invitation, John.
And for those of you still in the audience, I've got a couple poll questions up. If you wouldn't mind taking a minute and answering those. Um, If you would like a copy of this particular webinar, the webinar was recorded, and so I will, if you'll send me an email, I will send you a link to the webinar, and also PDF of the PowerPoint slides. So feel free to email me with that. Next, again, I've got my LinkedIn address up here, so please feel free to connect with me there. And Philip, if you're still with us, I think there was one other question that I didn't get to.
Uh-huh.
It's probably a pretty quick answer, but it's which organizations are you working with in Central America?
Okay, I'm working with Catholic Relief Services, who is helping organize different universities in El Salvador, Honduras, and Nicaragua. And so we're just getting started on the, the organization of that particular project. And what we will do is we'll be training the scientists in that area on how to use this technology, as well as completing the version 1 map for all of these countries. And so there will be a pretty big organization, lots of meetings, and a lot of coordination between the universities eventually and us, because we'll be doing the legwork on the mapping.
Okay, thank you with that, or for that. And with that, we'll go ahead and wrap up this webinar. Real quick, Philip, you got any other parting thoughts? Any other things you want to leave the audience with before we wrap this up?
Uh, no, other than we're having a lot of fun, and we're trying to improve and get better and grow and learn more about what we can do.
Okay, well, thank you very much. And thanks again to you in the audience.